ash was ejected from out of these channels and deposited close to the vent. There's another side of things which most people will know. PDCs have the capacity to climb significant topography, and there was in fact a radar station on one of these hills which got wiped out by a PDC climbing up over the hill itself. And this also highlights the danger of PDCs. This is approximately 12 kilometers away where the tail of the PDC is. And you can see quite close to here down the bottom, this is a structure, this is a dwelling. These are more kind of structures here. So this fortunately didn't cause any fatalities, but PDCs can be exceptionally dangerous and exceptionally mobile. And that's what we want to talk about in terms of the ash production as well. One of the examples of the danger and the mobility of PDCs is here. These are PDCs as they're advancing from Soufriere Hills volcano in Montserrat. Unfortunately, quite a number of people died in this particular event. And you can see that the PDCs themselves generate an enormous amount of ash, which rises from behind the head of the PDC. So PDCs are in fact the deadliest hazard. This panel B down here shows fatalities caused by different types of volcanic hazard. And the green color here is PDCs. And you can see that up to 15 kilometers away from the vent, they are by far the most dangerous or most fatal hazard. And they also a significant number of the total incidents involving volcanic hazards up to 20 kilometers from the vent. So they're a really key hazard that we try to study in order to try to better understand the threat from volcanism. This is a picture of a notorious event in Martinique. This was the 1902 eruption of Pelée, which generated a pyroclastic flow which was channeled directly through the capital city, Saint-Pierre, and resulted in the loss of tens of thousands of lives. And essentially the destruction of the culture on the island was absolute disaster. So there are really compelling reasons to try to better understand PDC dynamics. Co-PDC ash production is actually a much bigger deal than a lot of people consider. There's some pictures on the right-hand side here. There's Mount St. Helens. This was obviously a combined blast, but together with an enormous flow, which generated a huge ash cloud. So this is a classic event where a lot of the ash that was generated came not just from the blast, but from the subsequent PDCs and flows that were generated. It's not just enormous events like the collapse in Mount St. Helens. This is a dome collapse in Redoubt in 1990. So this is potentially a smaller scale eruption, but it also generated a large ash cloud that reached substantially into the atmosphere and generated a huge amount of ash. If we look at some particular events, so for larger events generate more co-PDC ash on the whole. I think that's reasonably safe to say. So for ignimbrite forming eruptions, co-PDC ash can be the dominant source of ash, and the source region of the ash can stretch for up to hundreds of kilometers. Estimates for the companion ignimbrite reach up to 60% of the total ash generated being co-PDC ash. For the more recent 91 Pinatubo eruption, ash was generated up to 20 kilometers from across the 16-kilometer length of PDCs. And during the 2006 eruption in Tungurahua, Ecuador, a similar fraction of ash, 58%, was also estimated to have come from PDCs for a BEI3 event. So across quite a range of eruption magnitudes, copyroclastic ash can be a significant contributor to the total ash that's produced and emitted into the atmosphere. I was involved in a small event in Santiago, Guatemala in 2012. I was camped here pretty close to the volcano. And there was a dome collapse on the far side of the volcano, fortunately for us. It was a lava flow which was oversteepened and collapsed down the flank of the volcano, and generated a PDC to about 6 to 7 kilometers, or 6 to 8 kilometers perhaps. And this was the ash cloud that we woke up to early in the morning from the campground. And not too much later, the wind took the ash cloud over us and deposited a huge amount of ash over us. And this was a relatively minor event involving a relatively minor volume of material, which occurred at San Diego. So I was able to collect some of the ash from this event, and this has spurred on some of the research which I've been doing my postdoctoral work and in the PhD. So just a little brief overview of the structure of PDCs. An important point to make here is that actual observations of PDCs are incredibly difficult, and we know very little from actual observations of PDCs. What we know is mostly based upon models of PDCs and analysis of the deposits. But this is a pretty well accepted idea of PDC structure, that there's a density contrast as you go down into a PDC, and there's a basal load which has a much higher fraction of particles than a more dilute overriding current, and then an even more dilute, potentially buoyant current over the top of that. And what I'm investigating in this study is interactions within this lower part of the PDC, in the dense basal region, where particle-particle contacts are common, and friction is the dominant mechanism where volcanic ash is produced. I just wanted to also point out that the particle size which is produced within PDCs is generally very fine, especially within this friction-dominated regime. And the particle size and the sorting help to determine the permeability, so the permeability on this color scale here of this lower region, or of a portion of the region of the PDC. And that permeability determines the ease with which gas can escape, and therefore potentially the lubrication of the PDC, which may potentially be a part of the reason for PDC's exceptional mobility. So ash production and better knowledge of the ash which is produced in PDCs can help us potentially to directly look at some of the hazards involving PDC runout. So we're looking at PDCs which are a lot less dangerous to study, fortunately. There's this equipment that we've been using, which is simply a cement mixer. The only custom part of that is that we ordered the cement mixer with an unpainted drum, and we fitted a lid to it. We ran some experiments at high temperature, just simply using gas furnaces, little gas burners, to reach temperatures up to 130 degrees C. So we're not reaching necessarily the temperatures which are present in many PDCs, but we were at least able to reach over 100 degrees. And we preheated our material that we entered into the cement mixer in these experiments to make sure that we had a reasonably consistent temperature. We also used this small gum tumbler. So we used the mini mishmash, or mixing machine as we called it, and we did some experiments within this larger apparatus. The large apparatus was inclined at an angle of 33 degrees. And these are just some of the dimensions which we use to characterize the flow inside the PDC, inside the drum. So we did experiments, and we stopped each experiment at 5 different time steps, at 15, 30, 45, 60, 120 minutes. We chose different starting masses to enter into the drum. So rather than volume, we chose mass, and we did between 0.05 kilograms. This was what we entered into this small apparatus, and we did from 0.5 to 2 kilograms starting mass into the large mishmash. We chose 3 different starting materials: scoria and pumice. So pumice from Lachazet in Germany and Setsedach in the Azores, and scoria from the Valentano scoria cone in Italy. Just some notes about different scalings that are used in these tumbling apparatuses. One thing that's worth pointing out here is that the dynamics of tumbling within these apparatuses is very well constrained, especially for ideal materials. And that means materials which are usually spherical, hard, and do not produce any daughter products, and have a very well constrained grain size distribution. As usual in volcanology, we're dealing with conditions far outside the ideal. So what I'm going to look at is some of the characteristic scalings which are used within these more ideal setups, and then see how applicable they are to our setup and ash production in the tumbling apparatus. So one of the common scalings is the Froude number. This is the angular velocity and the radius of the drum which is being used. And this is essentially the inertial component of force on the particles over the gravitational force. So this is essentially a ratio of inertial to gravitational forces within the apparatus. There's also the characteristic velocity, and this has the average diameter, or a measure of the diameter of the particles contained within it. And then finally, a common scaling is the drum diameter over the particle diameter. So within a range of Froude numbers, you're in a regime which is classified as cascading. And there are some great images of this regime here on the right-hand side from a recent paper. This is where, as the drum is turning, the particles get lifted up the side of the drum until they reach a certain height, and then they fall down the upper level of the bed of the drum. And depending upon the particle characteristics and the rotation speed, this can become increasingly oversteepened. And so you have a increasing component of free fall or gravitational force component within the bed load. It's also interesting to point out that within the very center of the load, there's a minimal absolute velocity. So the entire bed load is circulating. And it's the interactions which occur both in this lower part of the bed load, where the normal force is greatest, and the top of the bed load, where the absolute velocity variations, or the impact energy, is greatest, that generate the ash within the load. So in our experiments, we chose to use a fixed velocity for all experiments. So we have a fixed Froude number, and that Froude number is nicely within this cascading regime. This is an image of one of the pumices, the Lachazet pumice. 2 kilograms entered inside the drum, and the drum was stopped shortly after rotating. And this is here so you can see what the sample looks like within the drum. And you can also see that there's this angle. So this is approximately almost horizontal, let's say. And this angle is the static angle of repose of a bed. And that depends upon the particle characteristics within that bed, mainly. And so this is an important factor to measure. And beyond this is a video of the Valentano scoria being tumbled within the cement mixer. And here you can see the dynamics which were pointed out previously. So you see this essentially circular motion of particles being dragged up and then slumping down or cascading down. And this is a very is a very low fill, and so there's a significant interaction of wall effects within that. And there's almost all the particles are in continuous motion. But you can see with greater fill, you get more of a contrast between the motion towards the outer edges of the fill. So we took images of particles before they were entered into the drum and after each step of tumbling. And here's some images of before and after 60 minutes of tumbling. And you can see there's a really significant amount of rounding, which has occurred during the tumbling. And that rounding is associated with ash production. This is for the scoria. And you can see the same rounding is occurring, perhaps to a lesser extent than the scoria. And that's probably something to do with the sorting of the clasts and the hardness of the material. So these are results of ash production. So the weight % ash produced during the experiments at different time steps. And we've converted these time steps into tumbling distance. So this is in meters. And you can see that the ash production is greatest during the initial phase of tumbling. And then it tapers off as you increase tumbling distance. One thing that I should mention is that we ran two types of experiments. We ran type 1 experiments where we kept the ash in after every time step. So after 15 minutes of tumbling, we removed the material, we sieved out the ash, we weighed it, and then we re-entered the ash into the drum and continued to the next 15-minute time step. We ran 50-minute time steps up to 60 minutes and then ran a final 60-minute time step. This is what this jump is. So the type 2 experiments were where we took the ash out, we weighed it, and then we reserved it and only re-entered the solid lapilli-sized pumice or scoria back into the drum. And you can see from this image that these type 2 experiments where we removed the ash at each time step generated substantially more ash over time than the type 1 experiments where ash remained inside the drum. And that's because the ash which remains inside the drum helps to dampen the impacts between particles. We also ran these experiments in the small setup, and they have pink lines down the bottom here. And you can see that actually they follow the trend of the larger apparatus experiments pretty well. And finally, here in this light orange, there is 2 experiments which we ran at elevated temperature. The symbols denote different initial weights entered into the apparatus. And you can see these almost perfectly match the room temperature experiments. So within our apparatus and our conditions, we didn't see, at least within just these 2 experiments, any deviation from the room temperature experiments. The last thing to point out here is that higher starting masses were correlated with higher ash production. That was consistent throughout. So I'm going to skip now to the results from the 3 different materials we used. So this is the Lacazette pumice, and we ran the greatest number of experiments with that material. Then we also ran Setsudachi pumice, and these results were very similar to the Lacazette results. They actually produced the most ash of all experiments in this type 2 experiment here. So we had 53 weight % of the initial starting mass was converted into fine ash during just about 6 kilometers of tumbling. And we ran the Valentano experiments. And you can see the Valentano experiments, they seem to have a slightly different shape in terms of the ash production, with much greater ash production in the initial phase, and then it tapers off to a greater extent later on. And we had in just the first 15 minutes, so about 750 meters of tumbling, we had over 15%, so even up to above 20% ash production in some cases. So there's really significant ash production in the denser clasts over short distances of tumbling. We looked at the ash production rate. So we looked at the ash which is produced per every 100 meters of tumbling and how that varied with time. And we saw some really interesting trends. So in the type 1 experiments, you have this drop off in the ash production rate. So you start off with a particular rate and that really flattens out, that plateaus. So the production of ash, the rate of production of ash decreases with increasing tumbling. Whereas when we looked at the type 2 experiments where we removed ash at each stage, the ash production rate continued to drop off throughout the period of tumbling. You can see it really nicely here in panel B with the Setsudatch. The Valentano behaved a bit differently in that in all cases, the ash production rate decreased with time. And that's likely due to the higher density and higher energy interactions between particles within the Valentano scoria. We looked at the size distributions of the fine ash which was produced. And one of the things to point out here is that it is very fine. So this is about 100 microns, 125 microns, and essentially 80% plus of the ash which was produced was finer than 120 microns. There's this interesting small secondary peak here, which is most likely related to phenocrysts being liberated during the tumbling within the apparatus. We ran laser particle size distribution on the fine ash which was produced. And this is a micron scale at the top, phi scale on the bottom. So we're going finer in this direction. And you can see that the peaks of the grain size distribution are in the sort of tens of microns. And we saw definite peaks depending on the material used. And with increasing time steps, so we reserve the ash from each time step, go towards the left in this. So you can see that the ash produced gets finer with increasing tumbling. And these are for type 2 experiments. So that's probably to do with the rounding of the ash, creating fewer protrusions so that the energy which is imparted is only capable of fracturing off smaller particles as the particles continue to round. We also looked at the shape of the lapilli, which was being rounded, using the photographs that we took after each experiment time step. And you can see that that the solidity of the particles, so the convexity of the particle outline, essentially, increases with time. So you're removing concavities in the particles. And for the pumices, so the Setsudatch and the Lacazette, you can see there's sort of this tapering effect. So particles become more rounded and that effect diminishes with time. Whereas for the Valentano scoria, the rounding or the smoothing continues throughout the experiments. This is looking at results of the different experiments after 120 minutes, so after the final time step. And in the solid box plots, these are type 1 experiments. In the dash, they're type 2, and these dark colors are the initial condition. So you can see in all cases, the shape, the sorting of the shape is smaller for the type 2 experiments than for the type 1 experiments. So increased degrees of rounding, let's say, and less variation in the amount of rounding occurs if ash is removed from the system versus if ash remains inside. Form factor here on the right-hand side, by the way, is essentially a measure of the circularity or roundness of the particles. It shows similar trends to the solidity. I'm going to skip this part, but essentially we see similar results for the pumices, and again we see some slight variations for the Valentano-scoria. And on the whole, similar results for type 2 and type 1 experiments. After 120 minutes, that is. So we looked at whether we can correlate the shape with the ash produced, because they're obviously related. As you round, you're producing ash. And we plot the results here. So these darker colors are the solidity, and the lighter colors are the form factor. And what we can see is that there appears to be a consistent variation. But what we decided was the most convenient thing to do was to look at the change in the shape factor versus the change in the clast volume. And the change in the clast volume is essentially the ash production. And by plotting these, we were able to fit a regression. And it's a reasonable regression. So we found that the ash produced is 3 times the change in solidity squared, and that has a reasonable fit to the data. But there is still quite a bit of scatter in the data, and it's likely that a greater number of particles need to be examined than the amount we used in this study. So we took photos of 100 samples for each time step, and in the future I would try to take at least double that number, if not more, to try to get a better fix on the data. But this is encouraging because this is something we can use in the field. So if we're able to take photographs of field deposits and to get a good representation of the roundness of those deposits, we might be able to correlate that to the amount of ash which is produced. So here we normalize our results. And in this case, we're normalizing to, I chose 2 different normalization techniques. One of them is, this is essentially a 2-dimensional normalization to the flow. And I'm doing this by taking the distance, the flow, this is the distance of the flow and the height of the flow. So you can imagine this as essentially a 2-dimensional line down the center of the flow. And then in this case, I took the height squared as a really simple estimate of the volume of the flow. So this is the height squared multiplied by the length of the flow, divided by, in this case, the volume of the clasts, and in this case, the area of the clasts. So this is a normalized function. And then finally, this is a correction for the ash removal that we did in the type 2 experiments. So this is 1 minus the ash removed over the total ash produced within the experiments. So for the type 1 experiments, this cancels out, so you're essentially not correcting anything. But for our type 2 experiments, we were able to do this simple correction for the ash produced. And by doing this in the 2-dimensional case, we collapse our results pretty successfully, which was really great to see. For the 3-dimensional correction, we collapse really nicely all the results for the large apparatus into a single line, but we don't collapse all the results around a single regression. And the small apparatus didn't fit in with the rest of the results at all. So this 2-dimensional regression, so that 2-dimensional normalization seems like the most successful. And this is the gradient of that regression. So finally, we wanted to look at some other forms of normalization. So we looked at the flow rate, which can be simply calculated for a half-filled drum here. For a different fills, such as the ones we use, the filling angle can be used. And the flow rate can then be normalized. And in this case, we're normalizing by, this is the characteristic velocity, this is the height of the bed. And this can be related to the Froude number and this scaling of the class dimensions, the drum dimensions over the class dimensions. So using this normalized flow rate, we can use a paper by Chu and Lee, or we used a paper by Chu and Lee to look at some empirical results. They used a lot of different fills, a lot of different rotational velocities and Froude numbers to build up a database where they were able to look at so this is the dynamic friction angle, which can be calculated. This is the height of the flowing layer over the height of the entire bed. This is the velocity of the surface layer, so the layer which is cascading or tumbling down over the basal layer. And finally, using these data, we can calculate the shear rate. So this is the height of the flowing layer, which is calculated here. And from the shear rate, we can calculate the inertial number. This is the pressure, which is which we calculate using simply using this formula, and we can substitute that into the classical version of the inertial number to generate this as our calculation. So we plotted our results against this normalized flow rate. And actually, in this case, we found our best results were by taking the normalized flow rate, or the square root of the normalized flow rate, and then further normalizing it by the drum over the class dimensions. And in this case, we collapsed all data, once again, nicely for each material, but there are these offsets, these consistent offsets. And this is likely due to the fact that we haven't at this point considered intrinsic material properties, so variations in the surface roughness of the particles, for instance, the coefficient of restitution, which would need to be added to further collapse this data based upon the flow rate. But this is interesting because the d over d, which is added to the normalized flow rate, suggests a total scaling of d over d to the power of 3 over 2, because this flow rate already involves the square root of d over d. And this is something which is found by previous authors. So it's quite interesting that we find similar normalization with the ash production to previous work. And then finally, we plot our results against the inertial number. And in this plot, we again found that we didn't collapse data by any means, but we found that there was an offset with decreasing starting load. And if we connected data points with the same tumbling distance at different loads, we found that all of these data points converged pretty successfully. Here, around about on the x-axis, around about 3.6, and by taking this singular point, we were able to generate a formula for ash production just simply based on the distance, the tumbling distance, and the inertial number. So that worked successfully for the Lacazette pumices, and looks like it would work pretty well for the Setzer-Dach pumps as well, though we only have 2 data points. but it didn't seem to work so well for the type 2 experiments or the Valentinus scoria. So there's definitely more work to be done. But it was a very interesting observation that the inertial number, which is essentially a measure of the rheological behavior of the flow, seems to be able to be correlated with the ash production as well. So finally, I just want to thank Ulrich Kupers and his friends in Waakirchen for the retreat where we were able to do a lot of this work. And thanks once again to everyone involved in the study. And thank you for listening.
Thank you, Adrian. Thanks for the great talk. And my apologies, I should have noted you had a PhD from Liverpool before your Marie Curie fellowship. Yeah, we have time for questions and discussion, and please go ahead and use the chat function or raise your hand. And I have a question, but I see Yoshi has a question first, so we'll do Yoshi's. Did you run experiments? This is from Yoshi. Did you run experiments with dense class mixed in with the pumice, or with a very large dense class mixed in with the pumice? And he's curious if the presence of lithics would significantly enhance ash production compared to the pure pumice experiments.
Yeah, you're right. That's something we actually did investigate, and we were thinking along the same lines as you. I guess that's more likely to represent natural conditions in a lot of cases, and so we had type 3 experiments, which we didn't publish, but which we will hopefully publish when we have a more complete data set. But essentially, type 3 experiments, they produce the most ash, as you'd expect. And I can't exactly remember, but I think the change in ash production rate follows something similar to the type 2 experiments, in that it was reasonably linear throughout time, but it was higher than the type 2 experiments alone. So we used kind of large anorthosite clasts, sort of so big, in with the lapilli. So we definitely had a big component of milling there. And one of the things which I think occurs, which occurs in those type 3 experiments, is that rather than just abrading the edges of the particles and rounding them, you get a lot more fracturing of clasts. And when you fracture the clasts, you generate angular clasts again, which have a lot more capacity to produce more fine ash. So I think that's one of the reasons that you continue to see this higher ash production with clasts in. And I think that also occurs to a much greater extent in our scoria clast than our pumice clasts. I think there's more, wide-scale chipping or splitting of the clasts that occur due to the higher impacts between the individual clasts. I think that has an important role in maintaining the possibility to produce a lot of ash.
Yeah, thank you for the answer. And that was my next question. Did you count how many clasts you could observe were fractured? Because I saw, I think, one in one of the samples that you showed post-experiment. Did it seem like a significant number, or did some of them maybe get rounded before you could tell if they had been fractured in half?
That's a good question. It's not something we looked at carefully, but we can maybe look back at this quickly and see what we can see.
I think in the pumice sample, I saw one fractured class at least. Yeah, the middle left or row. There you go.
Yeah. I think that's quite likely, and this doesn't look necessarily like a natural shape maybe either, potentially. There's another thing which occurs, and that is potentially interactions with the wall of the drum, and some of this smoothing might be due to this particle being up against the wall of the drum for an extended time. But I would say this definitely looks like it's been split. And this one down here, this is a really nice straight edge, which suggests there's some splitting involved. And this probably occurs on the top surface of the bed load, or down on the base of the drum where the particles impact against either another particle or the edge of the drum. So yeah, even with the pumices, there is some degree of splitting, maybe even here as well. So that would be a cool thing to look at next time, to maybe spend a bit more time, yeah, characterizing the fraction of particles that are involved in splitting. But yeah, oh look, I'm missing this one. This is it.
Yeah, that was the one I saw originally. Yeah.
Yeah. Yeah, it would be good to characterize that and compare that with the changes in ash production, definitely. Yeah, thanks for bringing that question up. It's a great one.
Oh, very nice talk. Thank you.
The next question comes from Emily. Emily writes, thanks for the great talk. Could you speak a bit more to the nature of the analog spinning drum and how well it mimics the motion of particles in a PDC, to the extent that we know, as they are difficult to observe? Is there any evidence from observed eruptions that aligns with these experiments, estimates of ash production compared to components and characteristics of class as observed afterwards? And feel free, Emily, to jump in too if you like.
That's a really great question, and yeah, it speaks to the the applicability of what we're doing. Attempts have been made to characterize the particle properties, so the shape and the size of particle properties in PDC deposits, to the interactions within the PDC and for instance the run out of the PDC, with reasonably mixed results. I don't think there's been a study which has found a really great correlation to date, but a lot of the time these results are based on quite a limited number of class at any one place. And the other thing which I think needs to be taken really carefully whenever you're looking at field deposits is whatever the local conditions are at that deposition site. So any changes in topography will have a really important effect on the deposition at that location. And so it really takes very careful, I think, field work to be able to get valuable insights. And I think that would be a really fantastic thing to look at in more detail, taking deposits at different distances along a PDC channel deposit. I think it would take a lot of work and a really good appreciation of the local conditions at that point you're measuring. But I think one thing which could be used a lot more is, rather than direct sampling of deposits, taking images and doing image analysis could be a great way to get a much better statistical representation of the particles at a given point. So I think there's definitely potential to apply the particle characteristics and the PDC dynamics to a much greater extent that's been done so far. But to answer the other part, or to kind of address the other part of your question, how much do the dynamics within the drum replicate nature? I think it's a really hard thing to say with surety, but certainly with other granular flows which are investigated in nature, the dynamics within these rotary tumbling experiments are used more or less across the board as a good analog for dry granular flows. Volcanic flows, as usual, are more complex, and from what, as I said, direct observations are really scarce. But from deposit characteristics, I think that I think that the community in general considers that the sort of interactions that are occurring, so frictional contact interactions, which are occurring in the basal bed load, are reasonably well replicated within these tumbling experiments. But it's definitely a something that more attention could be paid to, and I'm not sure whether we have any upcoming technology or tools which might be deployed to try to get a better understanding of in situ processes in PDCs, but that would be one way that we could really start to better understand that question. But certainly there's a couple of things we don't replicate. For instance, we talked about milling, so having particles with very different sizes and densities within the PDC. The other part of that question is you obviously get continuous ash production and removal via the overlying ash cloud, as well as elutriation occasionally of the entire or a large fraction of the overlying cloud. And we're not reproducing that in the experiments, but we would like to in the future. We need to think about where we can emit a large quantity of very fine ash safely. But that's a cool thing to do, and that would definitely get closer to the natural situation. And it would also, you know, much better validate our results for high temperature experiments, where that elutriation might be affected to a much more significant extent at higher temperature. So those are cool things to think about for experiments in the future.
Seems like you've set a good groundwork. Thanks.
Thank you.
Next, we have a question from Larry Maston, and he writes, in thick PDCs, normal and shear stresses should be higher than in thin PDCs. And you'd think that this would round class faster. In your apparatus, can you easily vary thickness, and what are your thoughts about this?
So kind of, yes, indirectly, I think. Through changing the starting mass that we enter, we change the thickness of the flow. And you could see that from the images I shared of the, let me just, it's just before here. So this is 1 or even 0.5 kilograms possibly of the scoria, but this is 2 kilograms of the pumice. And we did 2 kilograms, 1 kilogram, and 0.5 kilograms in here. And by doing that, we effectively changed the thickness of the flow. And if you look at the results, you could see that the thickness of the starting mass was one of the primary contributors to the difference in ash production. So these results are universally ordered by starting mass, with a 2 kilogram in squares, 1 kilogram and 0.5 kilogram. So we definitely saw, if you take ash production as a proxy for rounding, which I think we can reasonably safely do, then we definitely saw greater rounding and greater ash production with thicker flows, which would make sense based on the energy.
Wow, thanks very much.
Thank you. That's good.
All right.
Sorry, I ran through those figures quite quickly, so it's great. Thanks, Larry, for giving me the chance to better.
Well, Adrian, I guess I had a question too, and you might have covered this too, but in terms of the textures of the ash that you produce, I don't know if you looked at this in any detail, and if you did, do you notice any differences from early in an experiment to later in the experiments?
The only thing that we really looked at in detail was the grain size. So I can speak to that. We didn't do any chemical analysis or anything else. But if we look at the grain size, so interestingly then, what we found was, so this color chart shows increasing tumbling distance or time, getting towards dark colors. And what we found here was that there's this secondary peak here, which is also associated with a reduction in this potentially phenocryst peak. So this is potentially liberated crystals within the matrix of the pumice. So there, perhaps at a certain point when you generate, so I guess the point I'm trying to make, which I didn't do a very good job of up to this point, this last time step is 60 minutes versus all the previous time steps being 15 minutes. And so even for the type 2 experiments in this step, ash was not removed throughout the entire period. And therefore, one of my thoughts was that the change in the rheology due to the addition of large fractions of fine ash generates enough shear stress within the bed to start fracturing even the phenocrysts. And that's why you see this peak start to be distributed towards lower sizes as well. That was quite a cool thing that we thought about. I don't have good micrographic evidence, but I think that was something kind of nifty. The other thing, so down here, this is the laser particle size distribution. Basically, for the 2 pummices, we saw fairly regular fining with increasing distance. And I think that's to do with the increasing average rounding of all the particles and the size of the daughter products which can be produced by a certain energy. I also have the type 1 experiments here in dashed black lines. So this is the type 1 after 120 minutes, and then this is the type 2. So you can again see that removing the ash generated finer, removing the ash from the experiments generated finer ash at the same time step. And then finally, for the Valentano scoria, this is the initial grain size distribution. You can see a really big change from 15 minutes to 30 minutes and then down. So we saw significant reductions in the average grain size and the grain size distribution with the scoria compared to these modest changes with the pumice. So that was interesting.
Yeah, oh, thanks. Yeah, and I had a question too, kind of related to this, and that is in the cases where you kept the ash with the pumice, do you notice much size segregation in the course of the experiment, or is it pretty well agitated and mixed?
That's a great point. We should have, and we didn't take any photographs or really look at the bed after tumbling, and that would be a really nice thing to do. Actually, I mean, the best thing to do would be try to get particle image velocimetry or something within the drum. But with the ash production, that becomes really difficult really quickly. But yeah, definitely the post tumbling analysis is that's a cool thing to think about. We didn't do that, and I hadn't thought about that. But yeah, that would be nice to look at.
Cool. Well, thanks, Adrian. Are there other questions out there that I'm missing? Well, thanks. Let's thank Adrian again, and for those that'd like to stick around, Adrian's been very kind to stick around for a few minutes here. If you have questions you'd like to ask us right at the end, just stick around, and as people leave, you can ask them and chat more one-on-one with Adrian. But thanks, Adrian, and again, next week, join us for the MCS webinars. I put the link there in the chat if you just want to click on that and register for that for next week. Again, that's Tuesday and Thursday, and if you'd like to participate in the Friday discussion, you can also register for that. All right, take care, everyone. Thanks, Adrian. That's great.
Thanks a lot. That was great to be able to present, and thanks for your attention and the questions. It's really nice.
Oh yeah, for sure. Yeah.